about to hear from Michaela, Roman, and Steve. They're going to talk to you about summiting the pyramid of pain.
Thank you. Y'all can hear me okay? All right. So let's begin. So we're here to talk about the future, right? Going with the time travel thing, and we want to think about how can we do things now that will make our lives far easier in the future. In particular, if you think about, Katie Nichols mentioned, do we want to keep chasing 0 days and all that, or do we want to actually calm down, think through our detections, and actually make something that stands the test of time? And that's what we're going to talk about today. But I want you to think about what can we do to improve our analytics and make the future of our analytics better. Very quickly, introduce.
Yeah. Hi, everyone. My name is MichaelaAdams. I am a senior cybersecurity engineer at MITRE. And in the spirit of time travel, we wanted to introduce our favorite time travel shows / movies. So my favorite time travel show is Loki. Please don't judge me. You can talk to me all about your criticisms after the talk. It's Sylvie's horn. It's the variant of Loki.
I'm SteveLuke, also a cyber person with MITRE, and my favorite time travel movie is Harry Potter and the Prisoner of Azkaban, one of the first movies that I saw, at least, where they kind of made the time travel events happen even the first time through that you see the plot, and I thought that was a really cool implementation of time travel.
And I'm RomanDaszczyszak, and that is how you say that last name. And my favorite time travel movie is Arrival, and you can debate me on whether or not you think that's time travel, but I would say that it is. Thank you. But enough about that. Why are we here today? Well, so some background, right? We have MITRE ATT&CK, right? We know all of the techniques that an adversary, or many of the techniques that an adversary will use, right? We can predict them. We've seen them over and over and over being used by adversaries. So, and we know that they're reused, right? They get reused all the time, every day. And we have tons of analytics out there. We've got repositories and repositories of detection analytics. So why are we still having issues detecting our adversaries? What's the challenge? Where is it breaking?
Speaking of breaking.
Right? Yeah, my apologies for the AV. We'll just keep going. Yeah. And then what we found very quickly is detection analytics, they leverage observables that are still easy to change. And what do we mean by that? Well, we're going to get into all of that very, very shortly. But why we're actually here then is, how do we actually score analytics? How do we actually improve our analytics? What would make them better? More robust to adversary control and adversary changes over time. So can we write one once and never have to write it again because we have that technique covered? We want to give you robust analytics for us, for all of you. So our talk today, we're going to go through the existing landscape of why we decided to focus on making analytics more robust. We're going to talk about how to do it. We're going to get into the technical details of that, the technical rigor behind it. We're going to actually go through and score a few. And we eat our own dog food. We like to apply what we do. We'll show you how to do that. And then we're going to talk about the future and where we want to go from here. And to do that, we're first going to talk about the background. Here's Steve.
So let's travel back in time about 10 years. It was a very good year for cyber TTP thinking. In 2013, David Bianco first published the Triangle of Trials, no, the Pyramid of Pain, to illustrate the different level of difficulty that an adversary would have in evading a solid defense that was oriented around these different kinds of observables that a malicious actor leaves behind, with, as we all know, at the bottom, the things that are easy to change, like hash values, and up at the top, the things that are most difficult for them to change, the TTPs, the tactics, techniques, and procedures. And also, in 2013, the first version of ATT&CK was published. And those go together so well because it documents those tactics, techniques, and procedures as are seen in open source reporting. So we've got this concept that is out talking about how it would be more difficult for the adversaries to change those TTPs and that defenders would get, therefore, a better return on investment if they could defend themselves at that TTP level. And now we've got a framework, thank you, a framework for documenting those TTPs and attack. So how's that going so far, right? It's been 10 years. How are we doing? Well, let's look at a use case to get some sample data. Let's look at Soloragate, since that was a relatively recent campaign by a pretty sophisticated actor who was clearly trying to be stealthy. So how did this whole approach work in that campaign? Well, we now know that the Soloragate campaign used 85 attack techniques. And even before the campaign was discovered, 79 of those techniques were already documented in attack. So big win for attack, right? They're doing great at documenting these techniques, and even with an advanced actor who's trying to be stealthy, they're reusing a bunch of those techniques. So it's like future Biff has come back to past Biff and given them the sports almanac with an ampersand in it. Very subtle reference there. And it's as if we've got this future thing that's predicting the future of the techniques that adversaries are going to use. Now, it's not exactly perfect like that sports almanac was, but it's pretty good. So it's a big success story for this. And here's a visualization of what that looks like in the Attack Navigator. Thanks to Jamie Williams for putting this together. And we can get a sense for the techniques and sub-techniques that were used. And in light purple, we see the techniques that already even had analytics written with those technique IDs labeled. And in dark blue, we see the techniques that did not have any analytic coverage. So not only was attack doing a good job of sort of predicting, that's not its purpose, but in effect, it was sort of predicting what was going to be used, but the defensive community had done a great job of writing analytics against those attack techniques. So to quantify that, 63 of the techniques had analytics that were already published just in MITRE's Cyber Analytic Repository and Sigma combined, right? Those are just the freely available open source analytic repositories. So that's great news. So success, right? So that means that a bunch of organizations must have downloaded those freely available analytics, implemented them, and detected Soloragate immediately before anyone else figured it out, right? No. And here is where the weak link, a weak link in the chain is discovered, right? When we looked at those analytics, what we found is that although they were associated with those attack techniques, almost none of them could actually detect the way that those techniques were implemented in that campaign. And that's because, largely, they were dependent on lower levels of the pyramid than just the TTP level. We're going to talk about that in a second. So the reason I have these glasses, it's your analytics, Marty. Something's got to be done about your analytics. All right, so with all that good news, why aren't we winning yet? Well, one of the reasons why is because, like I said, these analytics, although they do detect some implementations of the techniques, they're not really living at the TTP level. They're just linked to the TTP level, and they have dependencies lower down on the pyramid. And here's a little example. So in Soloragate, AD-Find was used for domain trust discovery, which was already a published technique, and there was already an analytic in Sigma to detect it. And here is a gist of that Sigma analytic. They had the command line contains and a bunch of command line arguments associated with AD-Find, and image ends with /ADFind.exe. So close, because if they just didn't have that "and" clause at the end, they would have detected the use in this campaign. But the malicious actor changed the name of the executable, and that's an easy thing to do, right? And the command line arguments were probably sufficient to narrow it down to just this one tool anyway. So it's kind of a brittle dependency for no real added benefit. So what can we do as a community to get a better understanding of where these dependencies are in our analytics? And what can we do to try to reduce the dependencies that we have on those lower levels of the pyramid of pain and get better at detecting things and live the potential value that we see from the pyramid of pain and from attack? Roman, can you talk to us a bit about what is an analytic anyway?
Yes, absolutely. Thanks, Steve. Yeah, so before we dive into exactly how to improve, we actually should talk about what an analytic actually is and some of the metrics around it. You have heard from other talks at Shmoo this time that we talk about precision, right? The accuracy of an analytic that detects a certain thing. We talk about recall. Did we catch all of the bad events in the query? We're actually going to be talking today about a related metric that's similar but not exactly the same as recall and precision, called robustness. And it is directly related to the pyramid of pain in terms of how much cost is there for an adversary to evade it? How robust is it to adversary changes, adversary control? And what we found in our analysis, how you actually construct the analytic has a significant impact on how robust something is to those changes. As you saw in the previous example, you can have an analytic that is focused on the right things, get all of the events, and then filter it too soon, or attach some sort of clause to it that then means that you actually miss most of the implementations of that. And so what are the components? Well, first of all, you have an event source, right? You get your data from somewhere, right? By the way, I wanted to back up. We are focused on analyzing Sigma analytics here. I want to be very clear. We are not critiquing Sigma. We love Sigma. They do an amazing work. They are a great service to the public. We're just here. We actually use them because they're available. So no criticisms there. Yes, we did score them. Yes, we did analyze them. Yes, we have some critiques. But overall, we're very happy to have the project. So besides event source, what else? Well, we have each field that you have in the analytic, right? And these are where we get the data and pair it to what observables are we looking for to get to detect a particular technique. And then lastly, we put it all together with some Boolean logic, right? And, or, not, XOR, if you're really having some fun with it. But we put that together, and that makes an analytic. But then, what about this robustness thing? Well, we need to break down the pyramid a little bit further. And for that, Michaela will take it over.
Thanks, Roman. So now that we've kind of broken down what an analytic consists of, let's go back to our original inspiration of the pyramid of pain and try to figure out where different parts, fields, values of an analytic fit into what we understand as robustness. So breaking down the first 4 levels of the pyramid of pain, we have hash values, IP addresses, domain names, and network and host artifacts. We group them into one general category of ephemeral values, which are easy for an adversary to change. Each of these values have differing levels of effort, time, resources needed to change them. However, they're very easy for an adversary to change compared to some of the other levels on the pyramid. Next, we have tools that are used by an adversary during an attack. If a defender has analytics that are focused on tools, an adversary may have to change the way that their tool behaves, or even just change the tool entirely to evade that detection analytic placed by the defender, making it a lot more effort for them to evade that analytic set in place in the victim environment. And then finally, we have behaviors demonstrated by an adversary. As Steve mentioned previously, adversaries reuse attack techniques. So being able to create detection analytics that detect at the behavior level, bless you, we are able to create detection analytics that are robust. and adversaries are going to have a lot more difficult time either creating new behaviors or changing their attack to evade those detection analytics that are based on behaviors, depending on what they're trying to accomplish within their attack. So now we have these general categories. We're going to go ahead and break them down into more specific ones, which will hopefully end up being our levels of analytic robustness we want to score on. So for that, we have our level 1, which is ephemeral, level 2, which is core to adversary-brought tools, level 3, which is core to pre-existing tools, level 4, core to some implementations of a technique or sub-technique, and then core to a technique or sub-technique. I'm going to give you a brief overview of each level right now. So the first, level 1, which is the bottom of our analytic robustness, is ephemeral. This is pretty much the same as our general grouping before. These are the observables within the analytic, so those individual components of an analytic that are trivial for an adversary to change, or even with something like hash values, they may even change even without adversary intervention. These are going to be very brittle in terms of being able to create detection analytics. Next, you have core to adversary brought tool. It was very important that when we were creating this that we break up the tool level or the tool grouping into 2 different levels. So this core to adversary brought tool is our observables that are associated with tools that are brought in by an adversary to accomplish an attack. If an adversary has control of the tool, if they've made it, if they have access to the binary, they can go in and change how the tool behaves, if like something like the PE header, the command line arguments, in order to evade detections that are placed in a victim environment. They have a lot more flexibility in terms of how their tool behaves, making it more brittle for a defender to detect those types of tools. So some of these tools may include Cobalt Strike, AD Find, even we considered PowerShell. Next, we have core to pre-existing tool. So kind of the opposite of core to adversary brought tool. These are observables associated with tools that are available to defenders before adversary use and difficult for an adversary to modify. We initially described this level as like pre-installed tools within a victim environment, but these are going to be tools that adversaries don't have access to the binaries or are able to change how the tool behaves. When they come into a victim environment, they're restricted on the availability of that tool and how they carry out their attack. So this is going to include tools that may be considered living off the land. The defenders have a lot more ability to be able to create those detection analytics based off these tools just because they know how it operates and the defender is restricted by that availability. Then we get to the technique levels. So first we have core to some implementations of a technique or a sub-technique. This is what we call the low variance level. So low variance behaviors are those which are unavoidable without a substantially different implementation. So if you go onto the attack page, an attack or a technique may have maybe 5 different implementations. If 3 of those implementations, maybe the same registry key is changed afterward, that is a low variance technique. It will capture some of those implementations, but not the whole thing. This is really important just because it will capture some of that behavior. Like on the SolarGate example, it may partially capture that technique, which is still useful for the defender to be able to capture some of that. And then finally, our highest level of analytic robustness is core to a technique or sub-technique. Differing from low variance behaviors, these are our choke points, which we call invariant behaviors. Regardless of implementation of a technique, it's going to output the same result. So let's say we have a technique with 3 different implementations of utilizing a GUI tool, a command line tool, or maybe even changing a registry key. And regardless of implementation, the same event code is produced. That would be an invariant behavior. This is the highest level of analytic robustness you can hit because no matter what the adversary does regarding the specific technique, they cannot evade detections for it. Now, we like to say on this team that not all attack techniques are created equal, just because some of these techniques aren't going to have invariant behaviors. If you take some look of some of the techniques, maybe let's say network service discovery, there's a lot of different implementations that might be very broad and not able to create those invariant behaviors, and that's okay. However, being able to map the analytic observables here, we are able to understand maybe where each technique falls onto this analytic robustness table and understand better where our analytics are in terms of their robustness for the individual observables. So we created these 5 rows, but we kept thinking something was missing. You know, we tried to add new levels, we subtracted new levels, we renamed levels, but nothing was really sticking. But then we realized maybe we weren't thinking in the correct dimensions. So Steve, what were we struggling with for a few weeks?
Right. Thanks, Michaela. So as Michaela talked about, one aspect of an analytic is the logic of what is the thing that you're looking for, right? Are you looking for the change of a certain registry key or something like that? And that's what these rows correspond with. But there's also, how do you know that that thing happened, right? Systems get instrumented in different ways. So there might be many different, for example, event codes that you could use to monitor the same underlying behavior, and they have different degrees of robustness intrinsically themselves. And that's really an orthogonal dimension to the logic of what's the behavior that you're looking for. So we wanted to acknowledge that and accommodate that in the model by having a second dimension in our model as well. So the second dimension tries to capture the robustness of the data source or event itself. Some events are triggered pretty high up in the OS stack. Some are triggered lower down. And so we're going to walk through the examples that we have in the model for each of these. So if these are the rows of our model, our second dimension are columns. And in the first column, we have the application layer. So these are events that are triggered by DLLs or other applications at the application layer in user mode that are triggering events. So for example, if you schedule a task using the task scheduler DLL, it will trigger a 4698 event. And so you will be alerted that someone has scheduled a task. However, if you don't use that library, then this event is not created. So one way that an adversary could avoid being detected by an analytic is not by changing the hash value or the IP address or even their technique. They could just go lower in the OS stack and not use the functionality that's been instrumented for the event that you're using in your analytic. And so in this case, they could just bypass the application and make direct calls to like the Win32 API. And so that's our second column here. There are other events that are triggered by invocation of user mode OS API calls. And so if an adversary is doing this, they're incurring a little bit extra cost, right? So this is a bit more of a robust analytic approach, but this is still bypassable. So something like syswhispers could make direct NT API calls, and then these user mode API functions are not being called at all. And so the events that are being triggered by those functions are not getting triggered. So your seams are going to see them. And no matter how robust your analytic logic is, you won't get the event to begin with. And so you've been bypassed. Sysmon event ID 1 is actually an interesting example of that. It's only being triggered by the OS user mode Win32 API call. But there are also events that are instrumented in the kernel mode functions, and an example of this is 4688. So event code 1 and event code 4688 are both process creation events, but if an adversary uses syswhispers, they won't trigger event code 1, and they will trigger event code 4688. So if we're looking for a process creation event, we will have a more robust analytic approach if we're using the 4688 event code instead of event code 1. So that's how we've kind of mapped the events onto this two-dimensional model. So Roman, how would we use this two-dimensional model?
Yeah, so again, how do we put it together? We've got analytic robustness, we've got event observables, put it together and we get a score. Well, before we can get to scoring, we actually have to think in a little bit more technical rigor about what makes a technique, how do you implement a particular technique, or how do you detect it? And for that, we actually leveraged SpecterOps' work and did some capability abstraction. And if you're not familiar with this, this is basically a breakdown. Across the top there, you have all the various attacker tools that they use to implement a particular technique. And this breaks it down in terms of various calls, various registry keys, various files, et cetera, that may have common implementations across, or may have common use across multiple implementations. So you start seeing how, when we talk about getting up to that TTP level of, can we get to core of some implementations or even potentially find a behaviorally invariant observable. So this helps you kind of map out where that might be and what API calls or what data it would involve. This is also a good way where we start thinking about where our sensor gets its data from, where do the events come from. As you break this down and you go lower, you can call Win32 API, you can call the NT API, you can potentially even go lower than that if you can get under the OS. But that's for a future talk. So just wanted you to start thinking about, break down the technique into what the actual implementations are, and look for those common pieces of data, common implementations. And then once we have that, first thing we need to do, we actually have to figure out where does our data come from. So we take a particular event source and say, okay, Sysmon, ID1, Sysmon, for example, gets its process creation information from user mode. So we're definitely going to have, our analytic is going to be somewhere in that column. And then we go through each piece of data or each observable that we want to place, and we actually place that based on, is it something that an adversary can easily change or control? And then map that to our analytic robustness levels. And then, of course, as we mentioned with analytics, you have to put it all together with Boolean logic. So how does that actually affect your robustness? If we take image ends with shtasks, for example, and command line contains create, and we add those together, what happens to the robustness? Well, image ends with, we say is level 1, right? It's relying on a file name. You can very easily change that. The adversary has full control over that selection. They can just rename the file and use it. And then we have command line contains create. Shtasks is part of the Windows operating system. The adversary cannot easily just recompile that. They could, then they'd be bringing it. That would be a different thing. That would be back into level 2, right? But, so it's core to pre-existing tool. You add those together, unfortunately, you drop it down and you get a level 1, right? And it together gets you the lowest score of all the fields and observables you've used. So what happens if you OR it? Right? And again, we are only talking about robustness here, right? This is not about, we first want to find them before we filter, right? So if you're thinking, oh, this is not going to be very precise, that's fine. That's a later one, but we want to first catch them and then filter down. You put this together with an OR, in our methodology, you get a level 3, because no matter what, you have the events from the ephemeral level, but you also have those in the query, so you have at least found them. So now, let's actually get into a little bit more concrete example of that. That's the general flow, and here's Michaela to explain that.
Thanks, Roman. So now you all understand it, so now I'm going to give you a quiz to actually score new analytics. Hopefully you ingested all that pretty quickly, but right now we're just going to go ahead and score some, and just to be clear, this took us a lot of time to figure out the best way to go about doing it. It's a new concept to pick up, so it might take some time once you go in and score your own analytics to pick up and understand easier. But for now, we're going to step through some of our analytics. So we're going to go ahead and take Steve's favorite attack technique, which is schedule tasks, and score an analytic based on it. So this is one of the schedule task techniques or analytics that was found in Sigma. And we're going to go ahead and walk through the steps that Roman just described. So first, we are scoring the event source. Right now, we have our log source as a process creation event, which is coming from Windows. This is not helpful at all, just because, as Steve mentioned, there are multiple different event sources that include process creation. So when we were first trying to apply this model and score our own techniques, we kept thinking, well, we need to think in what the analytic author intended. How did they want this to operate? Well, not to be rude, but it doesn't matter what the analytic author intended, just because when we put this into our analytic environment, it's just going to spit out whatever happens with it, right? So when we are going in and doing this, It is fully dependent on the fields that are present within the analytic. The relevant fields will determine what values pop out when you actually go in and place this within your detection environment. So after doing some analysis of the fields that are present in this analytic, we determined that the event source that is coming from is Sysmon, and the Sysmon event ID for process creation is event ID 1. And as Steve mentioned previously, we determined that create process A is called, which is a Win32 API call, and that operates in user mode. So this is going to be in column U. Next, we have the fields. So starting with the first field, we have image ends with shtask.exe. And I think as we've iterated many times in this talk already, this is an ephemeral value just because it is very easy for an adversary to go in and change the file name. It is not going to take that much effort. It is not actually like looking at the binary, just the file name. So this is going to be placed at level 1. And then level 3, it's the actual command line arguments that are part of shtask.exe, which is part of the Windows operating system. So this will be placed at core to pre-existing tool. And then we have applying our Boolean logic. So at the bottom of our Sigma analytic, we have the condition is the selection and not the filter. Within the selection itself, as we saw in the previous slide, it's separated by like the different lines and usually the dashes. We treated those as and operators. So it's going to be and for image and command line. We also have this part at the end of this, which is and not the filter. And I think this is a good time to bring up that throughout the duration of this project, we weren't really looking at the filter part too much. We understand that filtering is part of the precision of being able to score how precise this analytic is. However, just due to the time constraints of our project, we weren't really able to get around to doing much more research on that. However, we understand that it does have somewhat of an effect on how an analytic is carried out within the environment. So hopefully later research we can look more into that. So back to this. This analytic uses an AND operator, so the lowest level observable is going to determine the level of the analytic. So placing this through the model, Sysmon event ID 1 is in process creation, user mode column. We are then going to place the individual fields, so the command line argument is going to go at core to pre-existing tool. We then have image ends with task.exe at ephemeral level. Anding those together, the final score of this is a 1U. This does not mean that this is a bad analytic. It just means it's a little brittle in terms of its robustness. So it's great to know that we now know how much of this analytic is going to catch. It may catch some events, but it's not going to capture the whole schedule task technique. But what's also great about this model is that we understand maybe where some different observables are placed both in the rows and where the robustness of each event source we're collecting is coming from. So maybe that gives us some room for improvement. So I think Steve has some examples that he can walk through with us.
Thanks, Michaela. Right, so it's easier to criticize than to create. And a piece of advice that Adam Pennington gave me back when we were doing the Solera Gate analysis was, don't just say that these analytics aren't robust, but let's come up with some ones that really are more robust. So let's walk through a spectrum of robustness for how to detect task scheduling. So we've just seen one that's a fairly common approach, which is looking at that process creation, image, and command line arguments. And we've seen that we would now score that as a 1U, so relatively low robustness. What can we do to improve that? And we're going to walk through 3 categories of how we could improve this. One is to change the source of the data that we're using. So we were using event code 1, and we've already seen that there's another process creation event that's triggered by functions lower in the stack. We could also change the fields. So we could use different parameters that might give us more robustness as well. And then finally, we can change our Boolean logic. We can look for different types of things in the analytic, regardless of which event source we're using. So let's go through some examples, because it's all fine to talk at this high level, but when we have examples, I think this will make it a bit more concrete and understandable. So the first thing we could do, so let's go slowly through the spectrum here. The first thing we could do is we could change from using the field image to the field original file name. The original file name field in Sysmon event 1 comes from the PE header, not from the name of the file on disk. So even if, as Roman was pointing out, you change the name of the executable on the machine, that PE header value will still be shtasks. So this means that in order to evade that kind of analytic, the adversary would have to mess with a pre-existing tool. So that removes that row 1, level 1 dependency that the analytic originally had, and it brings us up to 2 components that are both at level 3. So that brings our whole analytic up to level 3 and increases the level of robustness just by changing that field. So this gives us a 3U instead of a 1U score. We're still using that same event source, so we're still in the U column. This could still be bypassed by doing a process creation more directly, but we've now gotten up to row 3. What else could we do? Well, we could change the event source that we're using and use event 4688 instead of event 1. That shifts the whole thing right from the beginning from the U column into the K column for kernel mode. And 4688 also has a command line field, and so we can still look for that /create. Although 4688 does not, last we checked, have an equivalent of the original file name from the PE header. So we can't use that anymore. So we see the first example where there's a trade-off between increasing robustness and maybe decreasing precision, because now this will detect any process creation where it has a command line argument /create, not just shtasks. So if we had a different tool that had a command line argument /create, it's going to trigger this also. So we're going to have more false positives in this simple example. So this gives us a 3K, right? We've gotten a little bit more robust because now we're in the K column, but we've seen that we've probably lost a little precision. What else could we do? Well, when you research task scheduling, you quickly find out that there is a built-in Windows event 4698 that gets triggered whenever you schedule a task. So that seems perfect, custom built for our purposes here, right? So that shifts us up in row to row 4, but the 4698 event is triggered by the task-sched DLL, and so scheduling a task without using that library won't create this event. So we've now kind of snaked our way up the matrix, and we're increasing the level of robustness in rows, and we're bouncing back and forth in column with our event source. Now, this particular event is a really good one because since it's custom built for task scheduling, it's got a bunch of metadata about it. Who scheduled the task, what user will be used when the task is run, what command will be executed. So lots of great metadata in here for detecting not only that a task was scheduled, but what was the task scheduled, so we can distinguish malicious from benign task scheduling. Now here's an example where on the blue side, during our research of how this technique works and doing capability abstraction, what we found out is that you can bypass this event because the invariant thing is that you must set a particular registry key. The task scheduler will just check that registry key and go execute whatever is in that key. And so you don't need to use that library to schedule the task as long as that registry key gets set. So we had the hypothesis of, well, maybe there's a way to just directly set that registry key and get a task scheduled without triggering that event. So we used regedit, and we scheduled a task successfully by simply setting the registry key, which would bypass this event completely. So that brings us to our last idea, which is to use registry monitoring through the built-in Windows Event 4663 and look at that registry key. Now this brings us up one more level to something that is core to the sub technique. And this example is a sub technique because we're just talking about Windows task scheduling. If you set this registry key, you have scheduled a task. If you have not set this registry key, you have not scheduled a task. It's a one-to-one mapping, and that's what brings it up to that highest level 5 robustness. There's no way of evading taking this action. And since we're using an event that's being triggered by the kernel mode functions, it's difficult for an adversary to evade this just by going lower down in the OS stack. So here's an example, right, where we have the same thing that we're looking for, but by changing the fields we're using, by changing the analytic logic, by changing the event source, we have explored a big variety of different robustness levels for these events. And we've seen that sometimes that comes at a sacrifice of precision. And so what we recommend is that in an actual SOC, you would have a suite of analytics, some robust analytics, and you might have some that are a little less robust just to reduce false positives. All right, I think, so that gives us a 5K. So Roman, here we are, back at the beginning. Wrap this up.
Thank you. So here we are. At least in one instance, one technique, we were able to go from a 1U, very brittle, potentially very precise, but very brittle, only detecting one implementation of a particular technique, to something now that actually detects every implementation as long as you're using that built-in Windows functionality of Task Scheduler. So we found a behaviorally invariant analytic that hopefully will just take us into the future. Unless Windows actually changes how they do task scheduling, this registry key should be stable to adversary changes in control, making it much easier and continuing to allow our analytics to work in the future. So with all that, this was a lot of work. So we have a call for help here, because as you can tell, we talked about Windows, we talked about host analytics, we talked about a single analytic. There are plenty of other platforms out there. There's Linux, there's Macs, all of that. So we need your help. We can't do this all ourselves. All of our research is on the website, and it's on GitHub for submission. So we would like you to come and actually help us score event sources. If you're using these, come tell us. If you have a particular EDR that you're using, come tell us what the score is, and we can add it collaboratively together. If you are a platform developer, start thinking about what data you are actually providing in your events that are more or less robust to adversary changes. Can you come and score analytic fields? Put submissions in on GitHub. Tell us what the robustness levels are for particular fields in an event. Can you score an entire analytic? And tell us about that. Or if you want to critique us, come tell us why we're wrong. I would love to improve our methodology and hear where it can be changed, where it can be tweaked. We've done this for one area. We want to keep doing it, but we can't do it all. And there's a lot more of y'all than there are of us. So please come and help.
And those are not the only ways that you can help contribute to our project. So what was a cool impact after we finished this project in about October of last year? Sigma actually added a tag into each of their analytics that allows for summoning the pyramid score. So if you go into any analytic on Sigma, it will have a score for STP that is like a number from 1 to 5 and either A, U, or K. This is really cool just to see that we used Sigma analytics so much during our research, and now that we are able to help improve the robustness of those analytics. However, there are a lot of analytics in Sigma, and there's only so many of us. I think during our project, we scored about 40 analytics and improved about 3 to 4 analytics also. So there is a lot of different opportunities for help there. If you are a contributor to Sigma, or if you just want to get involved in the space in the community, go in and try to score your own analytic, and also help contribute to our GitHub repository as well if you find something in there that may help benefit our research. And that's about the end of the presentation, but just wanted to give a shout out about how we were able to conduct this project. So we worked with MITRE's Center for Threat Informed Defense, also known as CTID, which works with industry partners for R&D projects that improve cyber defense at scale. So our research participants here helped funded our project, and we also have some external contributors that helped with our research as well. But also wanted to give a quick shout out to the rest of our research team that are in the room and also watching online. So also a shout out to Michael Esposito, Antonia Pfeffer, Robert Scholl, and Ross Weissman. So hi guys, if you want to raise your hands. Hello. We all brought different skill sets to the table, and this project wouldn't have been successful without them. So thank you. And that's the end of our presentation. I think we ended with some time to spare. We're happy to take questions, and we also have swag up here, and I don't want to take it home. So please come and take t-shirts and stickers. Thank you.
Any questions?
Any questions, comments?
Critiques?
Thank you.
Thank you.
Thank you. Thank you.
Well, if that's it, we'll hang out here for a while. Feel free to come up and talk to us.
Yeah.
Thank you.